Okay, so what we're going to be going over today, if I can get ourselves back up to the beginning, is kind of an introduction to the idea of functional programming. What we've been doing so far would fall under the category of imperative programming. And imperative and declarative programming make up the two kind of basic categories of programming. So imperative programming, according to Wikipedia, is a programming paradigm that describes computation in terms of statements that change a program's state. And by program state, we can think of variables and their values. Um, Imperative programming, let's see. So defines a sequence of commands for the computer to perform. And that's more or less what we've been doing. So there's procedural programming, which is writing programs consisting of subroutines, and object-oriented programming also falls under imperative programming. In contrast to imperative programming, there's declarative programming. And declarative programming is a programming paradigm that's the style of building the structures and elements of computer programs that express the logic of a computation without describing its control flow. And so essentially, many languages applying this style attempt to minimize or eliminate side effects by describing what the program should accomplish in terms of the problem domain, rather than describing how to go about accomplishing it. So this idea of no side effects is going to be a key idea in functional programming that's going to make it valuable in the context of parallel computing and the multi-core computer architectures that are common now. So SQL is an example of a declarative programming style, regular expressions, and the functional programming that we're going to be talking about. So functional programs tend to be succinct, making them easier to maintain and debug, and importantly, kind of prove their performance characteristics. That being said, it is a very different style and can be difficult to get a handle on. It's something that I'm still struggling as I've tried to move from my several decades of imperative programming to learn how to work with functional programming so that I can take advantage of the parallel processing capabilities of multi-core architectures. So there's a variety of very functional programming languages out there, Haskell being one of the most famous, which is a purely functional programming language, OCaml, standing for Objective Camel, Scala, which is a Java-based functional programming language, Erlang, and Lisp being a very old functional programming language. Now, Python is not a functionally programmed language, but it does support functional programming with some limitations. Python is really an object-oriented programming language. Okay, so let's look at how we would do summation of a list of values, and we'll do it in a procedural fashion, an object-oriented fashion, and a functional fashion with Python. Okay, so let's start with the procedural example. Here we're going to define a function, sum, that takes as an argument L, which is some list. And then we declare a variable S, which we initialize to 0, and this is where we're going to store the value of the summation. And what we're going to do is we're going to loop through every value in the list that's getting passed in, and with every value we're going to increment, that is, change the state of the program by adding n to the variable s, and then we'll return s. So here just demonstrating that we can sum up the numbers from 0 to 100 and get 50-50. And so what's changing in this? Well, first off, we have a changing state because we've declared this variable s, and that value s changes in each loop of the program. We also creating this variable n, which is changing as we loop through the different values of the list. Okay, now let's look at an object-oriented example. And here we're going to create an inherited class, summable list, that inherits from list, and we're going to add to it a method called sum. And essentially we're going to be doing here the same thing that we did in the sum1 function definition, where we create a variable s, which we're going to initialize to 0, and the state of the program is going to be changing as we, in each iteration of the for loop, we add a value to s. And then we're going to return that to the user. So here we create a summable list object. We initialize it with a list of values from 0 to 100, and then we call the sum method. And just like before, we get the value 5050. So again, changing states. In this case, the variables s and v are changing state variables in the program. Oops, so we just scrolled off the screen with our functional example. So here we're going to define a function sum2, and in defining this, we are going to try to limit the use of variables that are changing state. And so we now, instead of using a for loop, we're going to use recursion, and we don't actually have any state variables that are being modified. Instead, we have a base state that we check and see if the sequence length is equal to 0. If it is, then we return 0. Otherwise, we're going to return the 0th element of the current sequence plus the recursive call, where we are passing to the sum to the remainder of the sequence. And if we call this, we get the value 5050. So again, emphasize the recursion has been used to replace loops, and there's no state changes in the function. The limitation here with Python becomes noticeable when we realize that Python has a limited recursion depth. And so in practice, we would have to use for loops within our functions within Python, because we could not guarantee that a recursion depth would not be exceeded. Okay, now let's look at another problem, and that's calculating Fibonacci numbers. And these are Python examples that are taken straight from the Wikipedia page on functional programming. So here we have a procedural approach where we define a function Fibonacci that takes an argument n. And so what we're going to do is we're going to print off the first n Fibonacci numbers. So we initialize two variables, first and second, with the values 0 and 1. And then we're going to loop over a range of n, where we're going to print first, and then we're going to calculate first and second by the Fibonacci rule, and iterate over that the n number of times. So here we have as changing state variables first and second, and then I. Here we're going to use a functional approach where we are going to pass in the number n, and here we're going to have keyword arguments first and second. And we have, again, a base state that if n equals 1, then we're going to return a list consisting of the first value. Else, we're going to return, in a recursive call, the first concatenated with the list that would be generated by calling the Fibonacci function with n reduced by 1. And now we're passing in the values, the current value of second as the first argument, and the first plus second as the second argument. You see we get the same values. A slightly different approach that we're returning the list rather than printing the values. Okay, so we've already learned some of the key ideas that are involved with functional programming in Python. The first is that we can do functional programming because functions are first-class objects in Python. Also, that Python allows for higher order functions, that is, functions that take functions as arguments and or return functions as result values. We're going to want, because we want to avoid change of state, when we do have variables declared, we're going to want to use immutable data types such as tuples and named tuples in our functional programs. But there are some new concepts and tools that will be important for our functional programming paradigm in Python that we haven't been introduced to yet. The first of these is partial application. So again, from Wikipedia, partial application refers to the process of fixing a number of arguments to a function, producing another function of a smaller number of variables. So given a function xf of x, y, and z mapping to n, we might fix the first argument producing a function of type partial f, which now takes as arguments y and z, again mapping to n, because we have already fixed what the value of x will be for this function call, and it's no longer a variable. So let's see how this works in practice. So Python has a package that's part of its standard library called FuncTools, or module, and these provide various functions that facilitate the use of functional programming in Python. And this is just the help function for the FuncTools partial function. And what this says is partial takes a function and then various arguments or keyword arguments, and a new function with partial application of the specified variables is returned. Okay, so we're going to use this. We're going to use the partial function to solve a problem where we're going to write a function. What our task is to write a function that's going to take a document and a list of regular expressions and finds all the matches for the regular expression in the document. And what I want to do is create a new function where the list of regular expressions is fixed. So some little background, we're going to get regular expressions and reports. So I've put up in the repository a pickle file that contains some regular expressions for identifying uncertainty terms. And so we're going to use pickle to read that back in to our program here, and then using the pe.sqlite file that we've used in previous homeworks to read in some example radiology reports. And here I'm just going to convert all the reports to lowercase. Okay, so I now have a list of regular expressions. That's what's contained here in uncertainty regex, and I have a list of reports contained in data. So I have a function that I've defined here that's match regular expressions. It has an argument report and an argument regular expressions. And what we're going to do is we're going to return a list of all the regular expression matches found in that report across all the regular expressions that we have. And here we can call it. Here I'm passing the first report, and that's going to be data 0, and passing it the list of regular expressions. Okay, so that's how it works with our initially defined function. And now I'm going to define a partially applied function. So I use the functools.partial, and I'm taking the function that I want to make the modified function for, and I'm saying I want to take the argument regs, and it's going to be fixed to be the values in uncertainty regex. And this will be a new function called PMR. And I can call it the same. I can now take the function PMR, pass it the first report contained in data, and I'm getting a new variable matches 2, and I can see that I got the same number of matches that with both ways, both with the original function call and with this partially applied function. So why would we bother to do this? Well, this is where we introduce the next functional programming tool, and that's map. So map is a built-in function in the Python namespace, and what it does is it takes a function and then it takes a series of sequences, and what it will do is it will take each of these sequences and apply the function that we pass to a function to each one of the elements in the sequence. So instead of applying the function to a single report, we can now take our partially applied function PMR and using map, apply it to every element, every report that's contained in data. And this is important because we had 100 reports, and we don't want to be creating a list of 100 duplicate copies of the regular expressions in order to have the size match here for map. So we can now take our partially applied function and find all the regular expression matches with a single call to map. So what we had 100 documents. Our resulting list of all matches is 100 elements long. And if we look at any individual one, this is just looking at the first one, we have a large list of empty lists. That means that particular regular expression didn't match anything in the document, and some of them are non-zero. So map is one of our main functional programming tools, and it's often used in conjunction with filter and reduce. So I have links here to the documentation in Python. So what filter will do is return all the terms in the sequence. In this case, I'm passing it the first result of all matches 0 that satisfy the function. And so in this case, it's whenever an element is true. And you see that for across all of our 90 regular expressions, the only one that matched was the phrase borderline as an uncertainty term in the first report. So here we're using lambda to define a small anonymous function. So this is creating a function that doesn't have a name. It takes an argument x, and it's just returning that this is true. And this is equivalent, has a default. If I don't pass in a function, it's going to, by default, return any element that evaluates as a Boolean true value. So I could use filtering to reduce my data size. Instead of returning all the non-matching or empty lists for the regular expressions that don't match, that I can use filter to only return the non-zero regular expression matches. So here, just going through the steps again, I'm going to create a partially applied version of this match underscore regs2, which I'm calling PMR2. And I can use it now in the same way where I map PMR2 to the data. That is, PMR2 will be applied to every element in my sequence data. And when I do this, I see that I'm getting the same results that if I look at the first result, the only regular expression match was borderline.